Welcome back, and now we're going to get some practice with simple harmonic motion. So you can read the problem here. The idea is that if we think about this hung vertically, you can think about it horizontally too, but I like to think about this vertically. So you have a spring, and then there's a block on the end, and we're going to say that this is the equilibrium position, and then what happens is that it's pulled 6 inches below its equilibrium position. So from here to here is going to be 6 inches. Okay, and then it says that after release, it takes 0.25 seconds to get back up to its starting position. So I'm interpreting that to mean right back up to equilibrium position. So it would then presumably, if it's in ideal conditions, it would take another 0.25 up here and then another 0.25 to get back up to there. Okay. Well, actually, and then it actually started down here, so it's actually 1 full second to get back there. Okay, so I think I answered the first question, what is the period? Well, if you release it, it would need to start and end here. Or actually, I'm sorry, to return to its starting position. I read that incorrectly. See, this is why we need to be careful when we read. And we also need to read carefully. So it says to return to its starting position. So that's like 1 full cycle. 1 up and down motion is 0.25 seconds. So the period here is just 0.25 seconds. Okay, so then frequency is 1 over the period, which is 1 over 0.25, or 4. Okay, and then amplitude, because we are assuming ideal conditions, the maximum that's going to extend away from this equilibrium position is going to be the 6 inches. So I haven't talked about whether it's positive or negative yet. We have to define that, but we're just going to say it's 6. Okay, mathematical model for the motion. So the big question is, in terms of sine or cosine, right? We have, and I'm going to come down here with it, d is equal to, we know the amplitude is 6, and then it's going to be something, and then omega t. I'll need to figure out what omega is in a moment, but that aside, is it sine or is it cosine? Well, am I starting, is the object, is the block starting at the 0 position at equilibrium, or is it starting away from the equilibrium? Well, the answer is away, so I need to use cosine. And specifically here, if I define this 6 inches to be down, so if I say that this is, positive d and this is negative d, well, then I better have a negative 6 to indicate that it's starting down at -6. Okay, last thing I need to figure out is what omega is. And as omega is taking the place of b, and we remember that the period, so period, we would compute as 2 pi over b, but b is omega. Here we can solve. Omega is going to be 2 pi over 0.25, so this should be 8 pi. So I can erase this, and this will be 8 pi. Okay, yay, I got that. And then now I want to graph this thing. Oh boy, this is going to take a little bit of practice, or refreshing. We go up to 6 and -6. There's no center line shift, and there's no phase shift, but I know that I start down at -6, and I know that the period is 0.25, so if I imagine out here 0.25, and here would be half of that, so 12.5 seconds, and then we go into quarters from there. Cosine is going to do that maximum or minimum, 0, and then the other one, max or min, and then 0, and then back to the min in this case. So my graph should look something like this. Okay. Lastly, we want to know the position of the block at 6.25 seconds. That really is as simple as evaluating. So this should be, I should actually write this d as a function of t. it's as simple as evaluating. So for the last one, if I look at D at 6.25, my work here is kind of messy. I apologize. I just have to take -6 cosine of 8 pi times 6.25 and evaluate that. And evaluating this, you get 6. -6, actually, I'm sorry. Which just means that it's stretched out at its maximum downwards. Okay, so that's kind of how you can do that one. And you should really do a sentence with this too. Alright, so just make sure to do that. Last one. Okay, simple harmonic motion is not just springs. Pendulums are another common thing that you can talk about being in simple harmonic motion because they swing back and forth. If you don't know what a pendulum is, Google it. But here's another example. So we have a merry-go-round. It has a diameter, and we know something about its how long it takes to do a revolution. And we want to suppose that the center of the merry-go-round is the origin. The rider is initially placed there. So the reason I left the space here is I like to draw. I need to think about this as a diagram. So if this is the very center of the merry-go-round, and then if I can manage to draw a somewhat regular circle-ish, so imagine that's a perfect circle. And it's diameter 10, meaning it's radius 5, and the rider begins down here, and we're going counterclockwise, or we assume. It actually doesn't much matter, but we assume counterclockwise motion. Okay, and so it would start here and then turn from there. Okay, and I'm just going to write down other key pieces. So it's 1 rev every 6 seconds. And that's all we need to know. I guess the diameter, so the radius here is 5. Okay, which I kind of have here. So this is 0 minus 5. Alright, so we want to determine a model for the rider's horizontal position at time t after the ride starts, and then part B is for vertical position. Okay, so this is interesting. If you think horizontally, right, the rider is going to start going this way, right? And then when they reach this point over here, which is 5, 0, right? Then they're going to start coming back. And then as they go around, they're going to come back and keep going, and then back and forth. Like horizontally, it's very much that oscillating type behavior. Okay, vertical, we'll get there. It's going to be the same thing. But anyway, so the question here is, so if we think about the displacement from equilibrium, which we define as x is equal to 0, okay, so in this case, x is equal to 0 is our equilibrium position. We're going to have some amplitude, and then we're going to have sine or cosine, and then we're going to have omega t. Okay, so first question, amplitude. How far do they move from the initial? Well, that's going to be 5. Okay, because they move this way. Now, this one, since the rider starts at 0 horizontally, this one you're going to have to start with sine. Okay, and then omega t. Again, this 1 revolution per 6 seconds is sort of telling you the period. Simply put, it's saying that the period is 6 seconds. So if we know that the period is 6 seconds, that means that the period 6 is equal to 2 pi over omega, or omega is pi over 3. Okay, doing the math there. So pi over 3. And boom, you're done. Part B, very, very, very similar. Okay, again, the idea here is that they would start down here, but then vertically, they would go this way, and then back down. Okay, so there you go. If we look at it from this perspective, then our amplitude is still going to be 5. We're going to have, instead of sine, we're going to have cosine, and we're actually going to start down at -5, right? And then our value of omega isn't going to change, and just pi over 3t. Okay, so there we go. Last question is, if it lasts for 1 minute and 14 seconds, where does the rider stop? So notice that both of these models are in seconds. So 1 minute and 14 seconds is 74 seconds. So this is just evaluating both of those at 74. And so here I evaluated both of those at 74 seconds, and so I got the coordinate 4.3, 2.5, and so that would be something like right here. Okay, just so we have an idea of where it would be on the merry-go-round. So not in the initial starting place at all. All right, so big ideas here. Keep in mind that simple harmonic motion does not necessarily need to be restricted to pendulums and springs, but there are other applications where you could apply simple harmonic motion concepts to as well.